Okay, so yeah, so this is a Lego. The purpose of a Lego is to control the DAC system and run the experiment and record data. This will be like the default view when you open it. Your system tab will kind of be the starting point, and we've got a list of different DACs that we support, and then we also have the training modes, which is what we will look at right now. So then, yeah, if you want to just start seeing signals, all you have to do is just hit stream. And then, so this is simulated spike data. And then we call it the monitor. That's like your oscilloscope. And then we also have workspaces. So as you get everything set up, you can save that. So then, like, you've got your DAC, it'll save the DAC that you have selected in your mode. So then the next time you open the app, it'll just be right into that mode. And yeah, to see data, all you have to do is hit stream, and then to start saving it, all you have to do is hit record. And then we also have the high level like usability features. We've got this modular tab system, so you could drag this down here, or you could full screen it, and then that sort of thing will be saved as well. And then we've got a bunch of different tabs which we'll go through, but those all can, do the same layout and saving and everything. So yeah, we've got like a full suite of oscilloscope controls to zoom in on your signals and format them how you want. You can do a bandpass filter just for this specific window, because you could also have like different monitor tabs open with different settings at the same time if you wanted. You can change the time span. We've got different preset views. We've got controls for if we try to persist the events that are happening as it's being downsampled for the display on screen. And then if you want to look at a channel more specifically, then there's a right-click context menu, and you can pop out an oscilloscope view. And then that gives you a few more controls, but now you're seeing this channel in a little bit higher detail. And
Okay.
then,
Would you mind opening the pop-out spike view as well?
yeah, so actually, before I do that, I will go to the spike grid. So the spike sorting doesn't start by default, but you can just hit that start button, and then now you'll see the spikes start to show up, and there's some visibility settings there as well. And then we also have our spike sorter control, where this gives you some indicators for if you're getting useful units out of it. So like your probe yield. So like what percentage of your sites you're getting units from. And then now you see these went from gray to being color coded. So then that indicates that these units are starting to be labeled. So that's where the colors come in. And then, so
So
yeah, we've got some
it's
heat maps here. What?
so it's clearly spike sorting in real time. Does it save waveform data and ISI and stuff like that? So I wouldn't
Yep.
need to spike sort after collecting the data. It's already done.
Yep.
Or
Um,
really?
so I just click this gear in the top bar, and so that opens the acquisition settings. And so yeah, you can choose to save its continuous data only by default, but you can save the spikes alongside or the spikes only if you want. But then you can also do offline sorting as well if you'd saved that continuous data. So anyway, so with that running, now if I open the spike pop out, then yeah, so now you've got a more detailed view of this as well. You can you can set the thresholds either by voltage or by standard deviation, both the upper and lower threshold. And then yeah, you can set some like window settings as well. I think you have to reinitialize the spike sorter for that in terms of like the width of the waveform that's being captured. And then yeah, I can click through different channels here. That one doesn't have any detected.
So is it showing everything that exceeds a threshold, or is it showing what it has determined to be the spike waveform for this? channel?
It is showing everything that's exceeded a threshold, and then it's color coding the ones that have been sorted into units. So I
Okay.
dragged this threshold line, or this threshold level, like really closer, so it's picking up this noise now. So that's like every threshold crossing event, but then it'll try to label them as units as well.
And you said these are simulated data. Is it real data or you just made it look like real data? Because I'm just wondering how well it would work on real data, I guess.
It's kind of a mix, or I mean, it's like generated by the system as it's running, so it's not replaying a actual recording, but the like events that are being injected are based off real signals. But yeah, so you can double click from the spike grid as well to open a pop out. Oh, and then I started to get some audio noise as well, so you can have the computer play audio for selected channels. I'm now using the arrow keys just to like scroll amongst them. That's the left DAC. So with the X DAC or the smart box, it will send the same channel to the analog out as a speaker jack in the back of the system. So you could listen to it from an external speaker, or you can listen to it from the host computer, which is what I'm doing right now, or you can, use a BNC cable on that analog out to send it somewhere. So that's spike sorting. One of the other main focuses are the probe views. So since obviously NeuroNexus is a proud probe maker as well, we have all of our probe models loaded in here. So if you select one, then you can see, yeah, you can see the wireframe view, and then this will give you some other features as well. For example, I can sort the sites by either X or Y. So now they are kind of in shank order. So each shank is grouped with its own color. So you can see the first shank is together here in the top of the monitor, and then the second shank, or maybe more useful, is doing it by depth. Ungroup all of those, and then do it by Y. Now they are ordered by their Y position, so their depth in the brain.
You had to stop streaming to make the switch?
No, you don't. You do have to stop streaming to change the probe model.
Okay.
And so building off that probe model, we also have signal metrics. So what this does is you have a group of different metrics that you can pick from, and then they'll be color coded with this heat map based on, with each site. So the goal is to make it really easy to see where in the brain you're finding good signals, because you can see the exact spatial grouping here, and then you can see the actual values in the table view if you want.
Well, I
Yeah.
have a question. In the midst of an experiment, there are so
Mhm.
many things I can look at, and I'm always overwhelmed by the sheer amount of just data flowing past my eyes. And maybe your software gives a lot more ways to look at it, but it's still just way too much. And so, what would make it ideal for me is if I can go back after the experiment and essentially like go back to where it was, and I saw that this pad was, you know, getting a lot of activity on it because I'm seeing the red circle right there on that first shank. Like if I could actually use the same software to sort of replay, is that an option?
Yes, absolutely. Yeah, we'll get to that. So we actually have a separate application called Vidiri, which is meant for that offline replay, or that like post hoc replay. Yeah, it has all the same visualizations in it.
And all the metrics that you're tracking right now, they're actually saved so that I could do analysis on those right away, right after the experiment. Okay.
Yep. Yep. So yeah, that was signal metrics. And then still building off the probe integration, we also have 3D models. So you can see the full 3D model of your probe as well. And you can actually simulate your experiment, and you can read off your micro manipulator parameters and insert the probe virtually into the brain. And then we've got the vertical slice of the brain with the different positions. So we've got, let's see, we've got a mouse, rat, macaque, and organoid models.
Does your software allow for creating a custom model? Because we work with birds, so this would be very
Um,
cool to have, but you don't have it, but maybe we could like create it roughly for ourselves.
we don't have something to allow the customer to create it themselves, but we could work with you to add it into our system. If you have files available that describe the brain geometry and everything, but then just show off the little region atlas indicator as well. And then, yeah, you can also view the same signal metrics on this 3D wireframe as well as the spike rates. So, yeah, that's the 3D model. And then let's see, we signal processing. So this is your suite of filters and referencing tools. So there's hardware filters where the amplifier chips in the head stage can implement a bandpass filter right on the amplifier. So this is how you control that. And then we call it data stage or visualization stage. So any of our other filters can be added for data. That means that your recorded data will already have it applied. For visualization, it just means that it'll be applied to what you see in the monitor, but it won't be applied to the raw data in case you wanted to like do something different in the post hoc analysis. And so we've got low pass, band pass, band stop, notch filter, common average reference, virtual reference, paired reference.
Do you have common median reference?
No.
Okay, that would be
That's the
good to
first time
have.
I've heard that
Oh,
request, but that would be a pretty simple one to add, I suppose.
yeah, that's always been standard for my previous labs pipeline.
Okay.
Yeah.
Okay.
And how do I get to an LFP view?
Yeah, so we don't have LFP in this version, but that is something we have in development. So we're targeting at least a beta version of that by next month to have either power spectral density or current source density or both. I guess so. Actually, that's a good question for you is what would your ideal LFP view look like?
Well, all I have experience with is the view in the Inten software or the OpenEFIS software, which essentially looks just like what you have here in the filtered continuous trace view, but it just allows you to see it unfiltered or filtered differently to see the yeah, basically the waviness of the local field potential.
Oh, I see. Okay. So yeah, we do have a training mode for LFP as well. So yeah, you can see the waviness there. And then the field, so yeah, that's just a preset view settings. If you're just talking about the ability to have different like the IRR filters set, you could have you could have a two monitors like side by side or top and bottom that have like different settings, like one with your filters and one without it. And it kind of sounds like what you're describing. And then, yeah, like I said, we're also working on some spectrograph plots as well. Okay, so going to the last few things here. So we also have a raster monitor. And so this is, similar to your monitor, but just showing the raster plot view. And then, oh, right, we're in LFP mode. That's why we're not getting many spikes. But there will be the same spikes that you would see in the spike grid and everything just plotted here. I guess I'll point out the system tab is where you can set your GPIO controls. So I showed you a few ways to map the analog out channels, but you can do that here as well. You can set the gain. You can set your digital out channels. So we have a gated mode where it can just signal like when you're streaming and recording turned on. We have a manual mode, so you can just set them explicitly. The events mode will map them to thresholded events from your amplifier channels. And then we can also trigger recording on the digital in channel signals as well. But yeah, so I went back to the spike sorting mode. So we can see the raster. And then once it gets a big enough data set to detect the units, then we can see the neuron views. So yeah, this you can see the interspike interval plot, or you can also look at the average waveform, and you can control the bin settings as well. And then yeah, a lot of our views have you can export as a PNG to quickly save the results.
Yeah, I mean, during the experiment, I would likely never go into looking at all of these things. I would just be listening and watching channels with that seem to be responsive to the stimuli. But after the fact, that's when I would love to be able to explore.
Yeah,
Yeah.
totally. Okay, yeah. So that brings us to the companion app is Vidiri. So as I mentioned, this has a lot of the same views. So the new component here is the data files table. So you can look at all the different recordings you've made, and then you can click to open them for replay. So I could open a data set that I had previously recorded, and then I've got a DVR view or a DVR control at the bottom. So then you've got all the same components, but you can do it on the already existing file. So if I open the spike sorter, so this one didn't have a sort saved for it, I can launch the offline sorter and it'll give you progress on how many spikes it's detecting as it goes through the process.
So
Mhm.
it's kind of amazing, I guess, that it can spike sort because I mean, when I've run Kilosort 4, it requires a GPU and I have to run it. It takes a while. It just seems to be extremely computationally intense. But this seems almost casual. So I'm just kind of curious to know how that's possible. I mean, do you need a GPU, for instance, to run this off?
No, you don't need a dedicated view, or you don't need a dedicated GPU. You'll get smoother visualizations with GPU, but in terms of the spike sorting, no, you don't need one. Yeah, so I mean, we just have a fully custom implementation of the spike sorting, and yeah, we use a programming language called Go, which is really fast and really strong at parallelization. So yeah, that's how we're able to do the real-time sorting. I mean, it will definitely use a lot of your CPU, especially if you have a lot of channels, will use multiple cores, but we expect researchers to be using like powerful workstations to do their experiments and analyze their data and everything. Yeah, so that sort completed. I mean, this was just a short recording, but when you're doing the offline sorts, you can set some of your sorting parameters, feature dimensions, and the position influence versus the waveform influence. You can view the sort details. So it'll give you the high level statistics of like the number of spikes labeled versus unlabeled, the spike rate, and then for each site or channel, you can see the noise level and the spike count and the number of neighbors that were detected and the thresholds that were configured, because you can of course configure your thresholds as well, so you can do it at either via voltage or standard deviation at the port level because you've got a probe plugged into a port, but you can also do it at the channel level as well. If you pop one out, then you can set the thresholds for that specific channel or site. Oh yeah, I'd opened up HD Snapshot in the meantime. So I mentioned that you can configure the downsampling for the monitor, but if you want to see just every sample at a certain time, you can do that with this plot. You can just hover over the value of every sample. Yeah. So the signal metrics also available in Vidiri. So yeah, as you are replaying, you will get the same kind of heat map view, and with the 100 millisecond look back window, which is configurable. But so it'll be like, oh, from this time, 5.35 seconds in, then like here was our values with this look back window. Or you can also change it to be accumulated for the recording, like up through that point.
So everything we'll do in our experiments will involve a TTL pulse that is generated at the moment we play an audio stimulus. And so what we would most want in this post-experiment exploration is to go to each TTL pulse and then look at our list of stimuli and know which one corresponds to which pulse, so that we can see, oh, okay, here's what was happening at the time that this particular stimulus was played in the experiment. Is that all possible?
Yeah. What kind of recording durations are you going to be normally working with?
You mean for the whole experiment?
Sure, yeah. Or I guess that's another question. Yeah, are you going to be are you going to be like recording one long file or like breaking it up into multiple files?
I mean, I was imagining one file for like a 1 hour experiment during which we might play the same stimulus 20 to 40 times or 100 times or some number of times.
Within a Lego, we have an event view, so you can capture events like when a TTL pulse went high. Yeah, we are currently thinking about how to better visualize that over the full recording in Vidiri. Your TTL signal will be available. It's like whether when you're looking at it here in the monitor, like that's what these digital ins, you can see the thick bar on the digital out, like you can see the equivalent pulse on the digital in. And then we've got the event detection and the downsampling, so it will show up there. But yeah, that is something that we're thinking about is like a way to kind of like be like, oh, jump to next event, as well as labeling them.
Yeah, that'd be great.
Mm-hmm.
And if we could say like we're interested in event 1, 7, 12, 20, 25, because those are all one stimulus type, and then just go look at all of those. And then if we have a different stimulus type, we'll have different event numbers. Like just being able to manually enter that and then see them as a set somehow or move through them as a set would be very nice.
So when you say different stimulus types, will that be like on different TTL channels
No,
or?
it's a one TTL pulse whenever an event happens, which means whenever the stimulus is played, but we're playing wave files and we might have wave file type A and wave file type B because those are two different kinds of stimuli that are relevant to the animal. And so some TTL pulses will be associated with event type A and some with event type B, but it's all just wave files.
Right.
And
Yeah, that's interesting. Yeah. Okay. So we've had multiple conversations recently about integrating audio snippets. Yeah. So like the TTL pulses will definitely show up. And then you could also route your audio signal to the analog input as well. So then the actual sound wave would be recorded in the data file. So that would be interesting. But then, yeah, a way to categorize those by their waveform shape would be interesting. Could those audio snippets be like different? Are they like being generated somehow, or are they from like a fixed list of certain options that are being
I
like,
just to make it simple, just imagine you have a folder with 100 wave files in it, and they'll be played one by one in sequence. And amongst those wave files, there are two different types of animal vocalizations, but it's all randomized. And so when we look at the data, we want to know, okay, what kind of responses do we get to type 1 versus type 2? But as far as what we were playing, it was always just a wave file from that folder.
gotcha?
And so we'll know the sequence. So
Mhm.
type A was event 1, 3, 9, whatever, which then we can go look at the TTL pulse time. So that's what we'd have to do to analyze the data at all. But it'd be amazing if we could also just, because this program already analyzes a lot of the data. So if we could go one step further and say, like, we don't have to go through the trouble of like coding in Python our pipeline to integrate all of the
Mhm.
information about the stimulus sequence and type. If we could somehow just enter that into this and then move through each TTL pulse event and just see what was happening on every channel, that'd be amazing. But it sounds like you're not quite there yet.
Yeah, for sure. Yeah, I mean, yeah, that's something we would be interested in working with you on that because we definitely do that pretty often. Kind of like commissioning features for customers. So yeah, that sounds very cool because it's like, yeah, I mean, we definitely capture and sort waveforms on the amplifier channels, hence the spike sorting. So it'd kind of be similar to that if you were also routing those sounds to the analog in, but then yeah, not to mention just the ability to kind of scroll through the events as indicated by the TTL in channel. So then we do have one more application as part of the suite of programs, which is called Curate, where you can put a data source on there Say like, oh, I want my high pass filter. You can configure that. Then you can say, oh, I want to remove a shank, or you can also change the probe that was used if necessary. And then you could say like, oh, I want to see the difference between with a common average reference or without it. So then you could add multiple sinks.
Wouldn't some of this be dependent on whether or not you had these settings when you were recording? Because you can't unfilter something, right?
Yes, correct. That's why in the going back to a Lego, we had the different filter stages. If if this is something you're interested in, you could just use the visualization stage in a Lego. And so then it would be recorded without the filters, but you'd still be seeing them when you're monitoring the experiment. And then you could just go back and set up protocols to apply whichever filters you end up wanting to see. Or, yeah, and again, you could do as many different ones as you want, and then you could run this protocol. And then this is something where you can save this as well. So then this protocol will come back up next time you open the app, and you can create multiple ones. And then you can also do it for bulk data sources. So you could have it in one go, just do it for all the files in a folder, or whichever files you select. So that is curate. Yeah. So if I did the bulk source, then I could select a few similar files and then do the same filtering or referencing to all of them.
And like how customizable? It seems like it's these you have three filter types, and even the type of filter within each type is kind of preset, like how many, what order of Butterworth filter, that kind of thing, because there's just so many options, but you've kind of just predetermined all of that, right? Or can I go in and tinker with that?
You can change the order and the frequency cutoffs, obviously. But yeah, that's the
Oh, I see. There is a little thing for order. Okay.
Yep. So those are the options we provide for the IIR filters, are just the order and the frequency levels.
Can you give me a sense of what the saved data files are like, so that if I want to go and create my own analysis pipeline, like where would I begin?
Totally. So you mentioned Python. If you are a Python user, we do have a Radiens Pi package, which enables you to load all the data files. You can also use that to talk to the backends of these apps, like during the experiments. So you can actually implement your own closed loop controls. If you wanted to implement custom logic in Python, you could have something that was like actually reading any of the signals on the fly as the experiment's going, and then using that to like set the digital out channel or something like that. Or you can just use it to, open the file and analyze it in NumPy. And then we also have scripts that can convert it to MATLAB. Or if you want to if you kind of have your own pipeline and you want to do everything yourself, we have documentation for the file formats, which are very simple. So each recording is actually three files. There's the underscore data.xstat file, which is just the values encoded. We actually encode the voltages as 32-bit floats, because if you had done numerical processing like with the filters, then we just keep those full precision instead of putting it back to 16-bit. But then it's just a series of bytes for each of those values. It'll be like channel 0 sample 0, channel 1 sample 0, et cetera, et cetera. So it's just a flat binary file like that. And then we also have the xstat.json file, which is all the metadata in JSON format. So that includes things like which filters you had, file name, and the provenance and timestamps and everything, and the description of the probe and all the channels and the site geometries, site coordinates. And then we also have a timestamp file, which is the raw timestamps as well, just for kind of compatibility. That's not really necessary for if you're making your own Python script. But yeah, so that.
Is there a fourth type if you have TTL pulses for events?
The TTL signals are in the data.xstat. So they're just another channel type. And so the metadata is described in the JSON. But so the TTL values are in that same data file.
What kind of CPU requirements or other computational requirements would make this work without glitch. Because, I mean, I assume bandwidth requirements are high if you're going to be opening all sorts of different views and spike sorting on the fly.
Yeah, we don't necessarily prescribe a specific system. It really depends a lot on the channel count that you're doing.
Right.
A modern, like late generation multi-core CPU is necessary for sure. And then for like the graphics visualization, like a dedicated GPU is beneficial for sure. And SSD. But I mean that's yeah, so it's all pretty standard. We're so basically like if it's like a productivity workstation, you should be in good shape, don't, but not just like an old notebook or something.
Yeah.